Hello, I think we're live. I'm just checking. Please let me know if you can hear me, and welcome if you're just joining. So I'll just check we're all good, and hopefully I can see the chat. So yeah, welcome to anyone that's just joined. We're going to be looking at this web class on differentiation from first principles. It'd be great to hear from people in the chat if you're there, and that'd be great. Yeah, so welcome. Hope that's all coming through okay. Sorry about that. I just had a couple of little technical difficulties there, but I think we're up and running. And it would be good to just confirm that you can hear me. But that's great. So I'm going to just share the slides. Let me know in the chat if this is a topic you've done before, if you've done differentiation from first principles, or if this is completely new to you. And I'll hopefully be able to see those messages coming through. Let's have a little look. Brilliant. Okay, excellent. So I'm just about to share the slides and we'll see how we go. So, hi, welcome guys. Hope everyone's well. So first principles, hopefully you're able to see what I'm sharing now. And this is a topic that is kind of quite new to the A level. So since they changed the A level in around 2017, first principles got added in. And it's quite a massive topic really to have not been on the A level before. And now it is something that's very much examinable and a kind of a key focus. And it comes up in year 12 and 13. So do let me know if this is something you've done or not. But yeah, thank you all for joining so promptly, those that are here, and do feel free to ask any questions and share answers throughout. So I'm going to begin, and here we go. So I'm Max, I'm the lead maths teacher. I did a maths degree a while ago now, and I've been teaching A-level maths for the last sort of 8 years. So there's been quite a lot of change in that time in terms of the course and the way people are studying and everything. So it's been an interesting time to see that happen, that change. Right, so another thing just to mention before we get started, we have got the A-level exam crash courses coming up. So we're going to be going through loads of things, exam technique, trickier topics. There's a seminar booklet, tutor messenger. It's a really kind of fantastic couple of days for maths and certainly for the sciences as well. And it's taking place in person and also a live stream. So if you're interested in that, please do check that out because it's a brilliant kind of exam prep situation scenario for you. And we really meticulously go through all of the content for the exams. We try and really help get you exam ready, and it's a really good opportunity to do that over the Easter break. So that's coming up really soon. And it's, yeah, as I said, please do check that out if you haven't already. Right, so I'll mention that again at the end, but for now we're going to look at differentiation from first principles. So we're going to start by looking at what a limit is. Then we're going to look at how to use binomial expansions to find simple limits. And then we're going to understand graphically and algebraically what we mean by differentiation by first principles. So we'll start that now. Again, do let me know in the chat if this is something you have done before or if this is new to you. It'll be good to sort of see who has covered this topic before. So we'll I'm hoping that this pen will work as usual and we'll be able to make a start. So here we go. So what we're going to start with is we're going to start by looking at kind of the prerequisite stuff. So the idea of gradients. And when we talk about gradients, we mean the steepness. Oh dear. Sorry, guys. Oh, so binomial expansion is new for some people. That's fine. That's okay. So if that's something you haven't covered before, we'll talk that through. It's kind of to do with expanding brackets and looking at what happens with massive expansions and sort of how we can generalize using combinations. So that bit kind of might be new. What I'm going to do actually, guys, because I'm having a little bit of a technical difficulty with this pen, I'm going to reshare these slides if that's okay. So I'm going to just stop sharing that for a second. But yeah, binomial expansion for most people is new. It's not something you do at GCSE. So is kind of a prerequisite topic. So we're going to review that first. What we'll do is I'm going to just get a pre-annotated PowerPoint, hopefully. And then what we'll do is I'll show you kind of everything clearly through that. So first principles does come back with a vengeance in year 13, and it's kind of like done for trigonometry. So it's a real massive change for the A level, having that in the pure side of the course, because it's quite an abstract idea. Actual differentiation is quite nice for polynomials in year 12. So hopefully those of you that have seen that, you're quite confident with. So what I'm going to do, I'm going to just in a second share with you the PowerPoint again. I'm just going to load that up. But let me know if you've done the differentiation part, and if you've got any questions, we'll be able to deal with that as we start working through. But here we go. I'm just going to reload this up, hopefully. So apologies for the delay there. Hopefully, yeah, this is it. Great. Right, here we go. And if you guys could let me know if you can see this. And I'll skip back to where we were. Right, okay, here we go. So what we'll do, I'm going to just talk these through, and hopefully everyone can see that. Brilliant. Thanks very much, guys, and thanks for your patience there. So basically what we've got is we have the graphs here, a curve. The steepness of the graph is what a gradient is. It's a rate of change. Differentiation in terms of polynomials, that's all kind of a prerequisite knowledge as well. So for example, knowing that u times by the power and drop the power by 1 is really crucial. And then binomial expansion, some of you have mentioned that this is new. Depending on the exam board, like this will be in the formula book and stuff, but it is important to know that we can use the choose notation on the calculator to find out the number of combinations. So who has seen this before? Because this is probably one of the other newest ideas for most people. And we're going to need to use this in first principles. So it basically allows us to expand multiple brackets, more than just a quadratic or a cubic, but actually up to massive powers, and it works out how many combinations of the in-between terms there are. So all of this stuff feeds into this topic that we're going to be doing today. Now, all the exam boards are brilliant. Okay. Okay, so in terms of those that haven't seen N choose R, basically what this is if it was a 10 bracket expansion and you want the fourth term, 10 choose 4 basically shows you how many ways you can arrange 4 things out of like 10. So this does actually come up in probability as well for like massive tree diagrams in the binomial distribution, N choose R. And depending on your calculator, it's normally the button that has division, shift, and then that button gives you combinations. Some of the newer calculators, you access it in a bit of a different way. But we can work that through with some examples. So, as I said, this is on all the exam boards. This is a really kind of crucial addition to the new A level. So it's definitely a topic that's worth familiarizing ourselves with. Now, the first thing we're going to do, quite an abstract idea, no worries, that I don't think I met this until university, but limits, the idea of a limit. So we've hopefully all seen an asymptote before, for example, the 1 over x graph, the tan graph, but basically the limit of a function, f of x, as x tends towards a, is basically what we would call the limit. So the value that f of x gets closer and closer to as the value of x gets closer and closer to a. So basically, what's the y value ultimately doing as you make x approach a particular value? So who's seen that before? Who's seen the idea of a limit? Because again, quite new in general to the A level. But basically what this means is that as x approaches 2, as we get very close to 2 with our inputs, what's actually happening is the output is shooting off to infinity. And that forms a vertical asymptote there. So as we put values in nearer and nearer to 2, we're looking at the behavior of the graph locally to that point. Yes, so these are a little bit strange. You've probably focused on much more specific ones. So for example, here, as x tends to infinity, well done. For those that are kind of preempting where we're going with this, you may have seen it with h tending towards 0. That's what we're going to see later on. You're absolutely right. As x approaches infinity, for this graph, as x gets bigger and bigger, the horizontal asymptote, the value that the y value is getting closer to is 1, and it will never go below it. And we've all hopefully seen that idea before with asymptotes, but it's this notation we need to be familiar with. So we're looking at, as x tends to infinity, what is y doing? Or as we get closer to a particular x value, what's the graph basically doing? So let me know if that makes sense. Hopefully that's kind of clear. But I know for a lot of people, it's a very new idea. So we're going to look at limits, and then we're going to look at a few examples of this as well. And I'll talk that through. But yeah, really, really important to get to grips with that notation and understanding that it's kind of talking about what's happening as a process. So basically, here's a kind of fully annotated slide again to talk through. What we can do is we can split the limits up. So if there's a function plus a function, we can do the limit as x tends towards a of that function, and then do the other one separately. Now, what's happening here, just to note, and this does take a bit of thinking time. I think this is one of those classic maths topics where you have to sort of pause yourself and really make sure you've got it. So if we have a polynomial like x to the power of n, might be x to the 5, might be x cubed. As x gets closer and closer to 0, let's think about how that would behave. So if x is 0, and n is greater, so what would happen here if n is greater than 0, a positive number, as we get closer to 0, that whole thing will get closer to 0. So if I have like a really tiny number close to 0 cubed, it will get even closer, it will be close to 0 as well. So that's what that's saying. As we have, if we have n equal to 0, the answer will always be 1, because anything to the power of 0 is 1. And if we had n as a negative power, then actually, as this goes to 0, this is the weird one, x to the power of a negative number is actually going to get bigger and bigger, because it's like 1 over a fraction. So that's what negative powers do, and that will get turned into a massive number. So this is kind of a bit of a concept to think about. We're not overly going to use that specific case in what we're doing, but stuff like this is good for us to kind of work through and think, do I actually get what's going on here? Now, this part is really what we're going to use for first principles. This starts with a binomial expansion, this quartic. Is everybody happy that this is a quadruple bracket, just kind of in disguise? And we don't want to expand it like as 4 brackets really long ways. We want to use a little shortcut, and that's why we're going to use binomial expansion. Okay, so the way we do the binomial expansion is you would do 4 choose 0, which actually is 1, times by this to the power of 0. Sorry, what am I doing? Not that to the power of 0. Times by this to the power of 0, times by this to the power of 4. And ultimately, that would just become the first term to the power of 4. Because if you think about it, out of that 4 bracket expansion, the quartic term will come from the first one multiplied by each of the first of each bracket. So it'd be 3x times 3x times 3x times 3x. And there'll only be one way of doing that. Literally the first of each bracket times together will make the power of 4 term. Then after that, it gets a bit confusing because there's different ways of combining terms. So the next one, the x cubed term, will come from 3x times 3x times 3x times one of the 2's. And there'll be multiple ways of doing that. There'll be 4 choose 1. There'll actually be 4 different arrangements of that. And that's what this bit works out. It works out how many combinations. I've had some really good comments and questions. Let me just check. So is the variable always in descending powers? Brilliant question. It actually shouldn't really matter. It does for when you're doing binomial expansions to approximate stuff and sub stuff in. That is when it does matter. And then sometimes in that case we do ascending powers. But actually it shouldn't matter for this one, because you are going to need to do the whole expansion for this for what we're about to use it for. But they will normally state that if it's important. That was a really good question though. And yes, these numbers come from Pascal's triangle, these combinations. So hopefully that kind of clarifies how we'd expand that bracket. And then also we just tidy up this whole thing. So basically what I'm getting at, this first bit is how you would expand that bracket using the binomial. So that would be the first step. Then we've got to tidy it up. So then the question also said minus 16, and it also said it was all over x. So minus in the 16 cancels that. And then if you divide everything through by x, if you think about it, we've got a quartic. If we divide it all through by x, you're going to just be left with a cubic. And then we're looking at the limit of what happens as x approaches 0. Now, this is really, really weird because it does feel like everything should become 0. And basically, everything with an x does. So it almost seems like we're doing a lot of work and we're like, why are we doing this? But what will happen is, as x gets closer to 0, x cubed will get closer to 0. So that will ultimately get close to 0. And so what's happening is everything with an x in it is dwindling away to nothing. As I make x tinier and tinier, all the things that have an x in them are becoming irrelevant. They're becoming redundant. So the limit is kind of looking at the extreme behavior. As you get closer and closer to 0, what's disappearing and what's left. And you'd actually just be left with 96. So the value of this limit as we get closer and closer to 0 is actually the value 96. But you couldn't just know that looking at it. You do have to go through this very specific process. So we're going to see how this ties in with differentiation shortly. But if there's any questions there, please do let me know in the chat, because I would definitely like to be able to answer those, as I know this is quite a new idea for a lot of people. So yeah, that's where we're at with that one. But it's basically binomial expansion and then tidying up the limits and looking at how it's behaving. So the other thing to remember, which is quite nice about this, is they generally won't give you a massive expansion, like 20 terms, because they're not just testing that skill, they're testing first principles. So it's normally a quartic or a quintic or a cubic that you need to tidy up using binomial expansion. But we'll look at some other examples. Please let me know though at this stage in the chat how you feel with limits in general. So just a 1, 2 or a 3, and be honest and just let me know if you've got any questions. So the idea of a limit being like what's happening ultimately as you zoom in to a specific point, or as you go to infinity, what's the general behavior? So this topic, certainly for like Edexcel, this is the year 1 part of the pure, but this is basically what it is this will come back in year 2 as well, but it will be harder. So it's this idea kind of is in both. So we're going to look now at how to do differentiation by first principles, and we'll look at some kind of year 12 style questions to begin with as well. But the idea of a limit and the idea of first principles is actually in both years. So yeah, thank you for that question. Brilliant. Okay, so some people are a little bit unsure with limits, and we're kind of, it's okay, but it is a bit strange. And I agree, it's a very kind of abstract part of the course. Right, so here we've got some questions and answers I'm going to talk you guys through. And it says, evaluate the following limits for when x approaches 0. So I think this is maybe the thing people are a little bit shaky about with limits, is it feels like, can't we just sub x in as 0? And that kind of is like what you're thinking of. We're not definitively always doing that. We're sort of thinking, how does it all behave? What cancels, what disappears? So it is quite an abstract idea. But basically here, as x approaches 0, the denominator is getting really, really small. So for this first one, if we think about it, if you do 1 over 0.5, that would be 2. If you did 1 over 0.05, that would be 20. And are we happy that as we put a smaller and smaller number in the denominator, and you do 1 over that number, the answer actually gets bigger? That's the really weird thing with sort of asymptotes or reciprocal graphs. Is everyone clear on that? If you divide by a tiny number, you actually get a massive number. And if that is something that's never kind of sat quite right with you, for example, if you did 1 divided by 0.1, you'd actually get 10. Because what you're actually saying by the process of division is how many times does this thing go into 1? And the smaller it is, the more times it will go in. So as x gets closer and closer to 0, the y value actually becomes massive. And so the nearer you get to 0, that zooms off to infinity. So that first answer is actually infinity for that one. The next one is a little bit weird because we kind of need to tidy up the algebra and see the net effect of what's happening. So x squared times 2x squared minus 2x to the minus 2. If we kind of expand that and parts do cancel, you get a quartic thing, 2x to the 4 minus 2. And remember, we said we could split this. So you could think about the limit of this and the limit of this. Now, as x approaches 0, 2x to the 4 will go to 0. That's basically going to just get smaller and smaller, and that's going to disappear to nothing. And as x approaches 0 for this bit, well, it doesn't depend on x at all. So it's just minus 2. Okay. Let me know if that makes sense. And please do ask questions. As I said, I really appreciate the questions in the chat. They've been brilliant today. And please do keep asking, or if you need anything. How do you... Oh, very good question. So we have literally just expanded this double bracket. So basically 2x squared, x squared times 2x squared is 2x to the 4. And x squared times minus 2x to the minus 2, we've expanded a single bracket here. The 2 and the minus 2, remember when you add the powers, they would sort of go to 0, because it's basically x squared times minus 2 over x squared. So they sort of self-cancel and just leave us with minus 2. Does that kind of make sense? You can kind of think of it in 2 different ways. You can think of it as x squared. Sorry, this pen is dreadful today. You can kind of think of it as x squared times by minus 2 over x squared, which just leaves minus 2. Brilliant. Or you can add the powers, but we've literally expanded a double bracket. So thank you for clarifying that. I think that was really important for us to do. So the overall limit of that question was minus 2. Now, the next one, bit of a strange one. It says the limit of this thing here, x plus 2y all cubed minus 8y cubed over x, when x tends to 0. So this answer, all the x bits can kind of dwindle away to nothing, but we'll be left with maybe some y stuff going on. So if you triple bracket expand that, or use the binomial expansion, you'd get x cubed plus 3x squared times 2y, sorry, plus 3x times 2y squared, all squared, plus 2y all cubed. And then if we expand that and tidy it up, and then minus 8y cubed from it, this is what we get. And then if we cancel the x's, like we're dividing by x, we're left with the limit as x approaches 0 of x squared plus 6xy plus 12y squared. Now remember, if x is approaching 0, x is basically disappearing, then the net effect is we're left with the 12y squared bit. So it's very similar to what we were previously doing. Okay, so let me just move this on. So what we're going to do now is we are actually going to have a little look at using first principles. So this is really the new part. Because I think for some people it just feels like a bit of a random topic. And I want to now put this in the context of differentiation. So differentiation is allowing us to find the gradient function when we have curves. So a curve is obviously a gradient that's changing. The steepness is constantly changing all the way through. So what we're effectively doing is we know that a gradient is like the change of y over the change of x, the rate of change of y over x, change of output over change of input. So what we're doing is we're basically like closing the gap and we're thinking, how is the curve behaving in terms of its steepness? And the way to do that is through limits. So we think about a straight line, change of y over change of x, two coordinates, and then we're kind of shrinking that in and honing in on what's actually happening. And this is where limits and first principles is so powerful. So it's basically like the limit of the gradients of the chords from a specific point as the function goes. And we'll build this up and sort of show you how the first principles formula comes about. So here we go. So for example, when many examples give you this in the formula book, who has seen this before? So the first principle is the derivative of a function is given by the limit as h approaches 0 of f of x plus h minus f of x all over h. Who has seen that? And I know some people have because you've already mentioned the h thing. But basically what this is saying is that if you have an input x, the output is f of x, whatever it spits out, whatever the function is doing, the f of x is basically the y value. Brilliant. So some of you have. And what we're saying is if we made a small, tiny change in the x value in the input, so it's x plus a tiny amount, then the output would be different. The y value would be f, whatever the function is, of x plus h. So basically what this is this is change of y over change of x. The change of y is the difference in the y values on the top. The function of x plus h minus the function of just x subbed in, divided by the difference between x and x plus h, which is h. So it's kind of looking at the functional net effect of change of y over change of x, change of output over change of input. By making a smaller and smaller gap in h, we're looking at how this function is behaving in terms of its steepness. So it's a very abstract concept when you first meet it, because it feels like we're doing all this kind of fancy algebra and it works, but I'm not really sure why. And we have to kind of be clear that this is still just looking at rates of change. It's still just looking at gradients. And the point of the limit is that as we hone in, it's kind of summarizing what the behavior is doing of y over x, the change of y over the change of x, change of the function in terms of when we make a small change to the input. So what we do is if we took, for example, x cubed, many of you that have done differentiation will know that the derivative of x cubed is 3x squared. And most of the time in your exams, when they ask you to differentiate something, that is it. You don't need to use first principles unless they specifically say. So here, when we differentiate x cubed by first principles, we think if I made a small change to the input, I added h, x plus h all cubed minus just the normal x cubed output, all over the difference in inputs, which was h. As I make h smaller and smaller, closer and closer to 0, what is ultimately going on? So this thing we're taking limits with is h. This is the small change in the x value. As h approaches 0, the gap that I'm making between points is getting less and less. So if I expand the cubic and then I minus x cubed and I divide everything by h, so that will cancel with that, and then I divide all of these bits by h, I'm going to end up with 3x squared plus 3xh plus h squared. And remember, this time we were looking at the limit as h approaches 0. So anything with a h in it will disappear. And what we're left with is 3x squared. because that doesn't have a h, so that's not disappearing, that's not dwindling away to nothing. So our answer is 3x squared. So we've actually achieved the derivative we know is right through using first principles. Please let me know if you have any questions. Did that make sense? Does that kind of make sense what's happening here? As I said, it's a very abstract concept for some people because it's all like an algebraic net effect of what's happening. Welcome if you're just joining. Please do ask any questions if you've got any. And I know for some people, once you've seen this a couple of times or you've seen it before, there is a sense of familiarity and you think, right, I get what's going on. It might just be a skill I need to practice. But as I said, I personally think there should be a fair bit of emphasis in practicing this because it's one of those newer topics. So they basically want you to do that. It's like it feels like it's more likely to come up just because they've added it in. But yeah, it's something you definitely want to get to grips with. So let me know how you're feeling with that. Right, so I've had that question a couple of times. It's a really good point. This is the kind of year 12 side of it, but it comes up in both. It does actually come back up again in year 13. So it's in answer to that question, it's a topic that's in both years. Yes, very good question. It helps us find the derivative. It does help, it kind of explains how we do differentiation. It's how differentiation works. But it will also allow us to find differentiation at a point. The idea, though, of us using limits is basically to say we're kind of honing in on the behavior of the steepness at that point and describing it in a sort of functional way rather than just saying, oh, it's 5 at this point and it's 5.2 at this point. It tells us actually how the rate of change is behaving as its own little function. So for a cubic, the behavior of the gradients are actually following their own process, which happens to be a quadratic. And that's what we're working out. That's okay, no worries. Okay, thanks for that little checkpoint, guys. What we'll do, we'll look at a few more examples. So here's a kind of fully worked through one. And apologies again for the mishap with the annotations. We'll have to just use these pre-made ones today. But hopefully it's nice and clear, and do just ask if you need anything clarified. So there's the formula again, as the limits. And then we're doing x plus h all to the 4 minus x to the 4 over h. And if we double bracket expand that, quadruple bracket expand it, but use binomial expansion actually, this is what we get. And then we remember we're minusing x to the power of 4 off. Does everyone see that because this is a quartic function, x to the 4, then when we say f of x plus h, we mean that we're subbing x plus h into x to the 4 as the input. Because that's what the function is. This function is a quartic function. I'm putting x plus h into it, and I'm just putting x into it, and I'm taking them away from each other. Then I'm doing all of that divided by h. And remember that this is the limit as h approaches 0. So we're saying as we close the gap, and it's sort of dwindling away to nothing, the difference between 2 points that we're comparing the gradients for, how is the gradient behaving? So everything with a h will disappear. So if we minus the x to the 4, we divide through by h and tidy this up. Then we've got 4x cubed plus 6x squared h plus 4xh plus h cubed. And anything with a h in it, as h approaches 0, they will ultimately become redundant. They will tend towards 0 as well. As h gets smaller and smaller, they're dwindling away to nothing. And we're left with 4x cubed. And hopefully you guys are actually happy from differentiation that x to the 4 will differentiate, of course, to 4x cubed. You've probably learned that a much quicker way where you can just sort of times by the power and drop the power by 1. But knowing how to do first principles will allow us in year 13 to attack much harder problems than just polynomials and things that we can times by the power and drop the power by 1. It really is at the heart of how calculus works and how calculus behaves. So it is important to understand first principles. Right, is that okay? Let me know if you've got any questions there. Otherwise, I might move that on. Let me just check. Is that clear? So remember that the limit is the limit of h. We're looking at the small change in x that we call h. We look at that being the thing that's disappearing. Brilliant. And thank you so much for the comments and questions already today. They've been really useful for driving this forward. So very well done. So let me just move this on. So here's another example. Now, this is a really good one because hopefully what we can recognize here is that it says, given that that is the function, find f of 3 plus h, express your answer in that form. And when the end bit that people find a little bit weird, that Blackboard bold font, B and C belong to Z, the set Z. That Z is the set of integers, meaning whole numbers. Okay, so it's basically saying sub in 3 plus h as if it is x. That's what this means, and you might recognize this almost from GCSE, that it's saying the input is 3 plus h. Oh, sorry, that's not really working, is it? So we're putting 3 plus h into here as if it is x. So if the function is x squared minus 4x plus 2, it's a function that takes an input, squares it, minuses 4 lots of it and adds 2, and we're subbing in 3 plus h. We're going to get 3 plus h squared minus 4 lots of 3 plus h plus 2. And then basically expand that and tidy it up. And then what we would get as the output is h squared plus 2h minus 1. That would be what we would get out of that quadratic function if we subbed 3 plus h into it. And at this stage, you might think that's a bit of a random question, but it's going to lead us into the first principles. So let's move this on. Does that make sense? Any questions there with that? Is that all okay? No, do let me know if not, because I don't want to rush this on. And it's absolutely fair enough if that was it. So please let me know if there's a specific bit. So basically, this does seem like a bit of an out of nowhere question because we're gonna use it in the next part. Oh, okay. So what they'll often do with these questions is scaffold it in this way. So we've got the first bit, and then it says part B of the same question, the curve with that equation, x squared minus 4x plus 2, passes through the point 3 minus 1. So where the x value is 3. Brilliant, thanks guys. And the point the point Q is when x is 3 plus h. So using differentiation from first principles, find the gradient of the tangent to the curve at the point P. So they're basically saying, find the gradient of x squared minus 4x plus 2 when x is 3. Now, you could use straightforward differentiation, differentiate it, find the derivative, and sub 3 in. Many of you might also know you can actually fully get the number part just on your calculator. Does everybody know how to do the bog standard differentiation fully on your calculator? Most calculators do actually do it where you can sub a value in and get the value of the derivative. No, would you like me to show you that as well? Don't worry if not. So if you have the Casio Class Whiz, so this is the white back one, it is doable also on the CG50 and some of the other models. If you have this, then basically, yeah, okay, I'll show you this now. If you click on, and next to it, it says menu setup. Underneath that, there's like an integration button. Who has this calculator? Because it might be somewhere else on one of your other calculators, and I can talk about that as well. So if you've got this calculator, underneath menu setup, you'll see an integration button. So it will actually, brilliant, it will actually do bounded integration for you as well, and you just type the question in. So it's good for checking, but do bear in mind, like the exams will be aware you can do this. So if there's a lot of marks, you won't get it from just typing it in, but it's brilliant for checking. So if you press shift and the integration button, you actually also get a derivative button. So you press shift and that button, and it says d dx. Oh, okay. So I can't remember if that has it, but if you have an integration button, then normally above it is shift and then the derivative. Then you can actually type in using the X button next to the one you just used next to on, x squared minus 4x plus 2. And then if you use the across arrow and put x equals 3 and press equals, it will tell you the gradient at that point is 2. So that's kind of amazing because that's basically like a whole question and it will just work it out. It'll work out the gradient at a point on a curve. So it's differentiated it and it's also subbed in 3 and worked out the gradient is 2 at that point on that curve. And you might think, wow, that's exam sorted then. But obviously for this, we have to go through the process of first principles. Did you guys manage to get that? I just think it's a nice thing to show you because it's really good for helping you sort of be confident in the exam to check your answer because it would just do the whole question for you. Did we manage to get that? And likewise, if you have played around with that now and you've managed to get that to work, um, it's amazing because you're basically also got integration as well. So on the calculator, if you press shift and then the integration button, you should get a thing that comes up like d dx and then a box. And it asks you to, and then you literally just fill in x squared minus 4x plus 2. And then there's a little line and an x equals, and you put x equals 3 in. So let me just re-explain that. Let me just check that those that have this calculator have managed to do that because it's a really brilliant checking mechanism. So I might actually be able to show you on here actually if I stop sharing this for a minute. So if you're using this calculator here, underneath the menu setup, right, good question. There's a button with an integration symbol. And if you press shift and then that button, you get like a thing that says d dx. Now to actually type x in is the button underneath on has just a normal x. So you can actually type the algebra in. So you type x squared minus 4x plus 2. Let me just show you how I've written it like that. And then you use the across arrow to get to the little x equals, and you type that in at 3. And what this will do is when you press equals, it differentiates the whole thing and then subs in 3 as the x value and tells you that the gradient is 2, which is so handy for checking in the exams because it can deal with much harder things. It can deal with sine and cos and like logs and all sorts. It can differentiate anything at a point. So it's brilliant for checking. And that button also does bounded integration for you. So I think it's really important to be able to do that. Brilliant. Okay, so hopefully that's nice little calculator hack for you guys as a little checking mechanism. But I'll return back to the PowerPoint now. And I just hopefully that's been useful. Sorry, can you re-see this again? I'm hoping I've reshared it. Yeah. Oh, yeah, absolutely. Sorry. So I spent a bit of time explaining that, and we're thinking, right, that's me sorted for the exams then. You must know how to do it. I'm just saying it's fantastic to have a way of checking so you can move on through the paper confidently. Please do bear in mind, like the exam boards know what your calculators are capable of. So they're going to design questions where you can't just type everything in the calculator. But for your own kind of competence of using the calculator and feeling secure that you're doing well with the exams, it's so good that you can check your answers on there. And I just thought this was a good point to suggest and like let you know or remind you that you can use your calculator to do specific differentiation at a point. So I hope that was useful. But going back to this now, the actual skill of doing first principles, you should still achieve that result. Oh, okay. So if you wanted to do the second derivative, you'd, I suppose, type the derivative into there and it would differentiate it again. The thing is, this is only good for doing it at an actual value because No, so it won't give you an algebraic answer. Those calculators aren't allowed. It will only give you it with a value subbed in. So if the question said find the derivative and it wanted it in terms of x, it won't do it. But normally when you do differentiation, it's like, what are you doing it for? You're doing it to find a gradient. So you are usually using it to actually find a value, but it won't give you an algebraic answer. So those are really, really good questions there, guys. But here, hopefully we can see what's happened with this one is if we were doing it by first principles, we will get it in terms of h, we'll minus the output of 3, which was -1, tidy it up, divide by h, and then as h approaches 0, what's left? 2. So this is where differentiation by first principles has shown us that at this coordinate, the gradient is 2. Because the h's disappear, and that's exactly what we would expect. Okay, if you found that kind of calculator tip useful, that is sort of like the things we'll go through in the seminars that are coming up. So I'll talk about that at the end in a minute, but I do just want to make sure we're clear on here. So basically, going back to this question, no worries, I'll re-explain this because I realise we deviated a little bit. What we're doing with this question is we're using first principles to evaluate the gradient at a specific point when x is 3. Now, they've actually told us the coordinate is actually 3 minus 1. They've given us the f of x. The output is -1. If you wanted, you could sub 3 in, work it out, and you'd find that y is -1. But that would be a waste of effort because they've told you that already. They've told you the point is 3 minus 1. So the change in y, the change in outputs, is f of 3 plus h, which we just did in part A, and we got it in terms of h here, minus the value that comes out when we put 3 in, which is actually -1, the y value, over the small change h. So if we tidy the top up, h squared plus 2h minus 1 minus -1 cancels the -1, and we're left with h squared plus 2h over h. And then we divide the h's, we get h plus 2. And as h approaches 0, that limit approaches 2. So what we've done is we've done first principles, but we've done it specific to that particular coordinate. And we're saying that for that quadratic, when x is 3, the steepness has a gradient of 2. So it's not done it in general, it's actually done it for that specific point. So we've used first principles, but we've actually subbed 3 plus h in rather than x plus h, so that we can evaluate it for the coordinate 3. Very good question from Matthew there. Why does it say d dx? That is actually the notation we're going to get more familiar with, particularly in year 13. It's when you're given a function y equals, you'd write dy dx, but you're actually just doing d dx of y. So if they don't set it equal to y, you can just call it d dx. So if I said here's x squared plus 2, differentiate it, you can just do d dx of x squared plus 2. You don't have to go through the kind of rigmarole and the faff of calling it y and then doing dy dx. d dx means the same thing. But I take your point. We don't get into the habit of doing that in year 12 so much. But very good question. It is the same. Okay. All right. Excellent. Really, really good questions today. This is great. So hopefully, just to summarize this, if anyone's got any questions, you want me to go back to anything or explain anything, please let me know. I really appreciate your patience there today with like the pen not working so well and stuff, but hopefully that's all making sense, and you can also see how important this topic is. No worries. If you've got any questions, let me know. The one thing I will say that we've got coming up, and this is kind of incredibly soon, and it's also reminding me how close we are to exam season, because this term just flies by. We have got the A-level exam crash course coming up. And if you're interested and you like the kind of process of going through exam techniques and calculator skills and tricks and tips for exams, we're going to work through so much of the content in an exam focused way over those couple of days. Year 12 and year 13 content. So it'll be you're so fully exam ready. And they're always really enjoyable. Certainly from my point of view, these crash courses worked really well. And I would have loved to have gone to something like this or attended it virtually when I was at school, because it is nice to have guidance through an exam. So that is coming up. So in terms of tips, I think just having some sense checking techniques, so things like the calculator is really good. But basically, yeah, just make sure, like, especially with logarithms, it's easy to like make your own rules up. Make sure you're sticking very prescriptively to the laws of logs. But yeah, with differentiation, it is sort of just double checking it. And if you've got specific derivatives that you can check on your calculator, do that as well. But really, it is trying to sort of slow yourself down and sense check it as you go. Because the tricky bit with maths is when you have finished the paper and you think, right, I've got 10 minutes now to look back through it. It's very hard to actually see mistakes when it kind of all looks right. The time you're going to spot mistakes is kind of while you're doing it. You almost have to be self-critical as you go, and self-regulating, like going, I know this is something I slip up with, so I'm going to be super careful on this part of the question. I'm going to go a little bit slower than I normally do because I won't notice this mistake retrospectively. That's the kind of approach I'd be having. Um, and there's no real gain to having loads of time at the end of the exam, because you're not going to spot mistakes that have happened within a question. You're going to spot them at the time. That would be my advice. Sorry, it was very general, but hopefully that's useful. But yeah, as I said, we're going to be looking at trickier topics on these crash courses, and we're going to really look at exam skills. So modeling how I would work through an exam is something we'll be doing there. And if you are interested, it would be great if you can either attend in person or virtually. They're in the Easter holidays, and there is some information. There's some really good, useful booklets that you kind of keep with loads of practice that complements what we've put together really well. And it really allows you to tackle the whole A level. And it is kind of what it says on the tin. It is very much a crash course of the content. So hopefully, if you like the sound of that, please do check that out. We also have Tutor Messenger, so you can ask questions live as we're going through it. And that way we can kind of troubleshoot questions, much like we did today, as we go, which is really, really important for stuff like that. Yes, so there's a year 12 and there's a year 13 day. So yeah, this is open to everyone, anyone interested. There's actually the dates coming up. But I think yeah, there's a link there if you're interested in checking it out, with some more of the details. But they're happening throughout April for the different subjects and year 12 and 13. So year 13s may want to attend both. But yeah, we're really going through all of the content. And it'd be great if you guys can attend that. I'm really looking forward to it. Should be really hopefully useful couple of days. And yeah, every year it's been very enjoyable. So yeah, that was one thing I needed to say towards the end there. But thank you so much today, guys. Really, really well done. I'm going to stop sharing that there. Hope that's helped. Good luck to anyone who has exams coming up. So if you with your differentiation and logs test tomorrow, and anyone else that's in the kind of thick of doing exam practice at the moment. But yeah, really well done. And thank you all for attending and asking some brilliant questions there. I hope that's helped. Have a great rest of your weekend and hopefully see you at a session soon. That's great. No worries. Take care everyone. And as I said, if you're interested, check out the crash course dates and information, and maybe we'll see you there. That's great. Cool. Well done. Take care, everyone. Have a good week.